myself Ravi Kumar. Please subscribe our channel and share to your friends. In this video, I am discussing about the how to solve an unbalanced star load. That is, we know what is unbalanced. The load impedance will have different values. That is Z1, Z2 and Z3 which are connected in the form of star and has different values. Then how to calculate the different phase currents or line currents, voltages and current in the neutral wire, and what is the total power in the load. I am considering the example problem. An unbalanced 4-wire star connected load has balanced supply voltage 400 volts. Then the loads are Z1 equal to 4 plus J8 ohms, Z2 equal to 3 plus J4 ohms, Z3 equal to 15 plus J20 ohms. Hence calculate what are the line currents and what are the neutral current and what is the total power in the load. Then first of all, you can draw the star connected load by considering the phase sequence for the three phase is R, Y, B. This is R, Y, B, and this is Z1, Z2, Z3, and we know the values of Z1 is given 4 plus J8 ohms and Z2 is given 3 plus J4 ohms and Z3 is given 15 plus J20 ohms. Hence consider the line currents are IR and IY, and current passing through R phase R is IR, and current passing through Y is YY, and current passing through the B IB. Then all three currents are joining a neutral point. That neutral point we consider as IN. Then the current is passing through the neutral point is IN. You have to find out the neutral current also. Hence, based on the given values, first of all, what are the given values in the network? That is given Z1, the load impedance, that is 4 plus J8 ohm in rectangular form. You have to convert into polar form, that is 8.94 at an angle 63.4 degrees. Okay, in three-phase problem, every value you must calculate in both forms, in rectangular as well as polar. And Z2 value is given 3 plus J4 ohm in rectangular. We have to find out in polar form 5 at an angle 53.1 degree. And similarly, the third impedance 15 plus J20 ohm, then you can convert into polar, that is 25 at an angle 53.13 degrees. All are ohm. All are impedance value. The units of impedance is ohm. Then we know the impedance value in the form of rectangular as well as in the form of polar. Then we have considered the phase sequence is RYB, and given the line voltage, the three phase supply line voltage is given 400 volts. Then we have to find out phase voltage, that is V or N. We know the relation VL equal to root 3 VPH in star connection. From that, VBH equal to VL by root 3. Then the line voltage, the phase voltage is find out 230.94 volts. This is reference phase voltage. Then based on that, we know in three phase voltages, the given supply is balanced supply. That's why all voltage supply voltages are equal, but displaced by 120 degrees each other. Then similarly, VY1, Yn is nothing but 230.94 at an angle minus 120 degrees. And similarly, VBN equal to 230.94 at an angle 240 degrees. Here VRN is the reference voltage, that's why which is at 0 degrees. We know in three phase supply all voltages are displaced by 120 degrees each other. Then these are the values of supply phase voltages. Then from that we have to find out line currents. What are the line currents which are passing through RYB? And the line currents are, first line current is IR. We know that according to Ohm's law, V equal to I into Z. From that, I equal to V by Z. Then we know the phase voltages, that is VRN by first impedance Z1. Then the value of VRN is nothing but 230.94 at an angle 0 degrees by impedance value in polar form Z1 8.94 at an angle 63.4 degrees. From that, the value of IR is nothing but 25 point. You have to calculate that 25.83 at an angle 63 point minus 4 degrees, that is amperes. So when in polar form you make the division, then you have to calculate the equivalent angle value, that is phi 1 minus phi 2. Then the denominator angle which is going to numerator, which becomes positive changes to minus and minus changes to positive angle. In the same manner, the other currents, that is IY, other line current IY, then the voltage is for IY VYN by Z2. What is the value of VYN? The same voltage value is same 230.94, but the displaced angle is minus 120 degrees by the value of Z2 in polar form is 5 at an angle 53.1. Then we have to simplify that value. We will get 46.188 at an angle minus 173.1 degrees, that is amperes, that is minus 120. Then denominator positive angle 53, when going to the numerator becomes minus 53. That's why minus 120 minus 53.1, then total angle becomes minus 173.1 degrees. In the same manner, other line current, that is IB, the voltage for B phase is nothing but VBN by the impedance value Z3. Then we know the VBN value 230.94 at an angle 240 degrees by Z3 value in polar form 25 at an angle 53.13. Then we have to simplify the division. The value you will get 9.23 at an angle minus 293.13 degrees amperes. So this is the all three line currents IR, IY and as well as IB. Then after finding all three line currents, then what is the value you have to find out, that is the current which is passing through the neutral wire, that is called neutral current, which is denoted by IN. That is, apply KCL at neutral point, then IN is IR, IY, IB, all are entering current, and IN is the leaving current, and take the negative here, that is IR, IN equal to minus IR plus IY plus IB. Here, so neutral wire is there. Then IN equal to minus of IR plus IY plus IB. All we know the values of IR, IY, IB. Then what is the IR value in polar form? 25.83 at an angle minus 63.4 degrees plus IY value 46.188 at an angle 173.1 degrees plus at IB value 9.23 at an angle minus 293.1 degree. Then all are addition form. Then in order to add all values in polar form, you must change into equivalent rectangular form. Then the rectangular form of the current IR is nothing but 11.56 minus J 23.09. Then second one minus 45.85 minus J 5.54, and third one plus 3.62 plus J 8.48. Because these are the equivalent rectangular forms of IR, IY, IB. Then all are adding and minus term is there, that is minus. Hence, the neutral current adding all values along with minus also, then you will get the total value is 30.67 plus J 20.15 amperes in rectangular form. Then similarly, you have to change into equivalent polar form to find out the total neutral current. 36.69 at an angle 33.3 degrees, that is amperes. So this is the total neutral current in the star connected load. Hence, after finding total current values in each phase, then you have to find out the total power also. So before going to total power, you have to find out power in each phase. Total power, which is denoted by capital P. Then to find out the power in each phase, that is, what is the total power in or phase. That is, we know the passing current is IR and the load is R. That is the resistance value is nothing but R value, which is in Z1 impedance. That's why IR square resistance of the R phase. That is, IR is the magnitude 25.83 whole square. Then the resistance value in Z1 impedance is, that is 4. Then you have to calculate 2668.75 watts. In the same manner, you have to find out the power in other phases also. That is power in Y phase. What is the current passing through Y phase? Iy, that is I square, and resistance of the Y phase. Then we know the power loss across the resistance. The formula is I square R. Here using the same formula in each phase. Then what is the value of the Iy current? That is 46.18 whole square, and the resistance value is 3 for R phase, Y phase. Then find out the value is 6397.77 watts, and find out the same power loss in B phase. The formula is the current passing through is B phase IB square, and the resistance of B phase, that is RB. We know the current value is which is passing through B phase, that is 9.23 whole square, and resistance value which is given in Z3 impedance is 15. Then the total power loss is 1277.89 watts. Okay, this is the power loss across each phase. Therefore, total power in star connected load, that is total power which is consumed by the load, that is star connected load, that is which is denoted by capital P. Then what is the formula? Adding of all power, that is IR square R and IY square R and IB square R. We know the power loss in the R phase, that is 2668.75 plus 6397.77 plus 1277.89 watts. Then adding all values, then you will get 10,344.41 watts. So this is the total power loss in case of the given star connected load. Already we know the power values. We have to find out in this problem. We are finding all current values. In the same manner, we have to find out the every each phase voltage or line voltage. According to that, we have to find out the phase angle difference also between the current and voltage. Then we have to find out the power value. That is by using formula V I cos phi. That is root 3 VL IL cos phi, or 3 V phase I phase cos phi. That is total active power. In the same manner, we have to find out total reactive power also. What is the formula for reactive power? Q equal to VI sin phi. That is, you have to find out the root 3 VL IL sin phi. That is, VL is the line voltage, IL is the line current. From that, sin phi. You have to find out the phase angle difference between VL and IL between each phase. Then find out the total reactive power also. Then you have to find out the suppose apparent value you have to find out. You know the formula? Root 3 VL into IL. But here the star is unbalanced load. That's why we are finding current in each phase. The all currents value are not equal. That's why we are finding the power loss in each phase. That is in R phase, what is the power loss in Z1, and in Y phase, what is the power loss in Z2? In B phase, what is the power loss in Z3? Then by adding all power loss, we will get the total power loss in the corresponding star connected unbalanced load. Okay, in this way, first of all, we can draw the what is the star connected load based on the given values. Then we have to find out all values in terms of rectangular as well as in terms of phase angle, polar form that is. Okay. Please subscribe our channel and share to your friends.